Broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, and thank you for joining us on our call today. My name is Nicole Van Wert Quincy from Transcat, and I will be your moderator this afternoon. Our webinar topic is Solutions for Your Thermography Program. The topic is being presented by Ed Kahanick from FLIR. Ed's a Director of Sales for FLIR and is an ITC certified thermographer. Ed has been with FLIR for over 19 years and has spent most of his time helping customers get the most out of their thermal cameras. Ed has given training presentations for EPRI, Doble, and the Circuit Breaker Show. He has also trained some of the largest utilities in the U.S. in the proper and safe use of thermal imaging cameras in dangerous environments. We expect today's presentation to last roughly 30 minutes, and then we'll open it up for questions and answers at the end. During any time of the presentation, you can send questions through the question box, which is located in the right. I also want to mention that the webinar is being recorded. You will each receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. And at this time, I'm going to turn the presentation over to Ed.
Thank you, Nicole. Good afternoon, everybody. We're going to go through this Solutions for Thermography program presentation that I've prepared. But before I do that, I just want to give a note. I am fighting a bit of a cold. So if for one reason or another I put it on pause for 5 seconds, it's because I'm coughing. And I certainly don't want to have that on the webinar. But just so you know, I am fighting a bit of a cold. I'm on the tail end. And a cold waits for no one, so the show must go on. So if you already have a camera, if you've thought about cameras, to improve the reliability of your facility, there's a couple things you should be asking yourself, right? Do you need better imaging and resolution to quickly and easily identify a problem? Is your program to that level? How much of your work is actually outdoors versus indoors? That has an effect on the performance of your system, the performance of the targets that you look at, whether they're far away or whether they're outdoors. Also, doing a thermography program takes time. Do you have the right amount of time to conduct a thorough inspection of your facility? How can you improve that? Do you have new or inexperienced users? Did someone who you've had train all of a sudden leave for another position? Have they been promoted? These are all issues that when you start a program that you have to overcome through the life of the program. Many times I've talked to customers and that camera that they've invested in is locked into the closet. They only let one person use it, so they're never getting the most out of that camera. We'd like to see that camera being used as much as possible. If we can make that easy to use, then you'll get continual return on investment with that technology. Software. A lot of cameras come with software. Software is generally generic and very basic. Software is an integral portion of the program. If you have a smooth running program, you have a camera, software, and trained personnel utilizing this all in concert. These are all opportunities that if you've answered yes to any of these, then you should be considering doing something with your program to make it a little bit better. What is thermal imaging, right? I'm assuming most of the people on this call know what that is, but if you don't, it's strictly taking the invisible and turning it visible. This is one of my favorite pictures. It's a mechanical application. We have a spindle. If you walk by this is a motor. If you walk by this in your factory, in your plant, you would think nothing of it. If you had your thermal camera with you at that one moment, you would clearly see that one of the motors is much warmer than the others. And that is very simple what thermography is being able to do turning the invisible visible. Bear with me right now as I'm noticing that there's a bit of a lag on the PC. Okay, hold on. So all you need to know is and this has been true from day one, usually finding one problem like this one has a tremendous payback. I would tell anyone, most of these problems that you find cost into the thousands when you find it with a camera. So whether you spent $1,000 on your camera or $40,000 on your camera, you're going to get a good payback. But to the true justification of a thermography program that includes personnel, multiple finds improve efficiency and performance of your facility. This is where you go a long way in improving the way you either manufacture something or you service something. And most importantly, documentation. Do you have the ability to show an image, a report this week, next month, next year to people above you that you need to help justify the program so your facility can continue to run smoothly and efficiently? But before we go into what, how to improve your thermography program, I always like to start at the beginning. What is infrared? Infrared's part of the electromagnetic spectrum. As you can see by this chart, we use most of this spectrum throughout our everyday life. Right now, we're using the visible spectrum with our eyes, viewing this webinar. Right after visible wavelengths are the infrared bands. And within the infrared bands, there's midwave and long wave. We are currently manufacturing cameras predominantly in the long wave range. From your perspective, it really doesn't matter whether it's midwave or long wave. It's just that the technology is more affordable in the long wave. And then if you notice that this electromagnetic spectrum goes out further, you can see the microwaves. Microwaves are what we use every day when we heat up our food in our kitchen. So those wavelengths are actually longer than infrared. So how does it work? Every object in the universe emits infrared radiation. The hotter the object, the more radiation that it can sense. And inside the camera is a sensor that is sensitive to this radiation. So whether it's ice, whether it's a cold day in Vermont or a hot day in Arizona, that radiation from every object hits the detector. Now, our skin is also an infrared radiation detector, right? When you're outside on a sunny day, you can feel the heat from the sun. But you cannot feel the heat from your targets because the signal strength is not strong enough. Well, the signal strength is strong enough to excite the detector that's in the camera. And when it does that, it does create a picture. It gives you the ability to identify what is hot versus what is not. And then you apply your knowledge of what something should look like versus what it does look like. For example, in this very simple electrical application, the main conductor overheated to more than 220 degrees with only a nominal load. As you'd learn going down further, load has a direct impact on temperature measurement. But from a purely imaging standpoint, we would recognize that anything that's above ambient in this situation is a problem. And the payback here is if someone added the normal load to this situation, that temperature that was at 220 could easily skyrocket to well over 1,000 degrees. And if it goes to that point, that's when you have an explosion, you have a shutdown, and you have stop production, and you are now dealing with a situation that you didn't have to. Many times when I hear about electrical fires within buildings and industries, I always say to myself, I wonder if they had a thermography program. Because if they did, and they used it properly, they could have caught that. So this presentation is going to go a little bit more in depth about how to get the most out of your program. What are some of the hurdles that are preventing you from doing the very best job possible day in and day out, achieving that consistency and getting the technology to work at its optimal and to get the excellence out of this system? Because we want to see our customers who invest in our technology use it to its fullest extent. So the first place I always start with when I think about using an infrared camera is there's application indoors and outdoors. And I know from my smartphone, it's really hard if I'm outdoors trying to see what the screen is on my smartphone. And if I can't see the target that I'm looking at, how good am I going to be? As we see from this gentleman right here, he is contorting himself, bending over, trying to shield the camera and trying to see a target. If you're outdoors and you're looking at a disconnect on a utility pole that's delivering energy to your facility, if you can't see the target easily, then you may miss a problem. So one of the values of infrared is you really want to see what you're looking at. It adds time if you struggle with it. I'm experienced. I'm over 50 years old. About 5 years ago, I started to need readers. I used it infrequently, and now I'm wearing them right now as I'm going through this presentation. I know these are small little things that add up to making a program more challenging than it should be. Historically, infrared cameras have had eyepieces on them. Traditional eyepiece thermal cameras are expensive. Today, those cameras are quite affordable. And if you're outdoors, most people use sunglasses outdoors. Using sunglasses while you're trying to look at a screen makes it really hard, especially when you're using readers at the same time. So with today's technology, some cameras are now coming with both an eyepiece and an LCD. And that really helps to work at any lighting conditions, indoors or outdoors. It removes and reduces any sun glare. You never have to worry about it. It's auto on and off. You just put your eye up to the camera. The eyepiece recognizes that it needs to be turned on. It will turn on. If you move away from the eyepiece and look at the LCD screen will turn on as well. And for me, nice feature is this second arrow points to the radial dial where I don't need my readers because it has a magnification built in. And lastly, a split camera design with an eyepiece allows for comfortable viewing, whether it's indoors and outdoors, whether the target's above you or below you. And it's really a professional camera that allows a facility, a person, to get the most out of the applications that they're looking at. The next question I always get is, how hot is hot? And what I mean by that is, customers always ask me, well, if you see this problem and the reference is that problem or that issue, when should I monitor? When should I take it out of service? And the short answer is it depends on all the manufacturing equipment that you're looking at, because everything is designed to work at its own temperature. But I love this image because this image clearly identifies the value of thermal imaging. So right now I got a blue box over the temperature. And I always ask the question, what's the melt temperature of aluminum? I have a reference temperature of 114 degrees. If I'm doing everything correctly, if I understand my emissivities and reflectivities, and I'm understanding those parameters, I'm going to get really close to what that temperature is. But sometimes that temperature is so hot, I can't believe it. And in this application, this customer was lucky enough to discover that this hot spot was above 1,000 degrees. This was a ticking time bomb. But more mundane issues that you'll normally find, you'll find that the temperature rises are more subtle. And this is a chart that is provided by NETA. NETA is a testing organization. They put standards together. And the temperature difference, they've given you two ways to view it. Delta between similar components like A, B, and C phase, or if you don't have that, rise over ambient. So in this case, delta is based on 1 to 3 degrees. It's probably a problem. These problems don't go away. They just don't get better over time. So what this chart is telling you is over time, this problem will get worse. It is up to you as the decision maker how long you can run before failure. This chart gives you the ability to kind of window into that decision making. And it's something I find many utilities use something very similar to this. as a precautionary gauge on what they should do. So in certain cases, when they got a 15° C rise over similar, they are not going to wait any longer. They are going to take that out of service as soon as possible. But how do we ensure we are getting the most accurate temperature measurement possible? And to figure that out is what we have to do with our cameras and understand what our cameras are capable of doing. So in this case, we're seeing a picture where the camera has a focal plane array. So it's got pixels, just like your visual camera has pixels. 1 pixel in our parlance is called IFOV, instantaneous field of view. So here's another picture of a grid. And there are 3 popular sizes of arrays. There's 320 by 240, which gives you 76,800 pixels. There's 640 by 480, that gives you 307,000 pixels. And then there's the top of the line array of 1024 by 786 that gives 786,000 pixels. I'll get to the OR numbers in a second. But when I look at that graphic, I see that the IFOV is 1 pixel. All cameras give you the temperature measurement of the center pixel that target is on. So when you put a spot meter on, it's the center target. What we recommend is that customers fill that target whole, and we call that the MFOV, measurement field of view, which is 3 times the pixels. The more pixels you can get on the target, the better it is. And we're going to go through and show some examples on what temperature measurement means when you look at it with different resolutions. So what are the numbers to the right? What's the 307,000? Why did those numbers increase by 4 times? Because we're going to get to a solution that's built into these cameras that I'm not certain many people are aware of. But these cameras have the ability to increase their resolution simply by storing many images and then putting them together and coming up with a larger array map that gives you a far denser pixel map. And we'll show that in a second. So in this regard, here's a simple example of a product. If I have a small resolution camera, as you can see, 1 pixel does not fill the entire target. I see much of the background. So what the pixel is doing is averaging the cold and the hot and coming up with a 79.1 degree Fahrenheit. If I can have a camera with 4 times the resolution, that means I capture more of that target and less of the background. Consequently, the temperature goes up. The more pixels I add, the smaller the sample size, the more accurate the measurement, and now I'm at 120 degrees roughly. If I go back to the chart before, a couple of slides ago, you would see that there is a delta chart for reference over ambient and reference over like. As you can imagine, your decisions would probably be different based on the resolution of the camera that you have. Now let's talk about this other feature called FLIR's brand name is called Ultramax. Other camera manufacturers have other brand names, but they do something similar. And what Ultramax allows us to do is quadruple the number of pixels by taking a series of images, like you'll see right here in this animation, where these pictures will shift back and forth where we hone in on a much smaller temperature. So in this case, we were able to accurately go back, and I'm going to do this one more time so you can understand the concept. When I store the image, this camera feature will take 16 images. As you hold it, your hands will slightly move left or right unconsciously, and the camera will come up with a far better image. I've got a real good example coming up in a real live action picture. So this feature is currently on many of the modern day cameras purchased within the last 3 to 5 years. If you don't know about it, check your camera system or look for it under the trade name for FLIR Ultramax. What are some more basic ways of improving resolution? Optics. Now, sometimes you might want wider field of view, so we have wide-angle optics. Then we have the standard field of view, which is the 24-degree optic, and the telephoto view in this case is the 14-degree optic. Infrared optics are much more expensive than visual camera optics. So we actually have to put in separate optics per camera. We just can't do a telephoto or a wide angle within the same chassis. It becomes cost prohibitive to do that. So in this case, we're seeing a light right now for perspective of a 45-degree lens. If I put the 24-degree lens, you'll see I've cut the field of view in half, but I've gotten twice as close to my object. The 14-degree telephoto lens is what I'm looking at right now. So that is the standard optics that come with many of the FLIR cameras and many of the other manufacturers' cameras out there. And then we also have a super optic called the 6-degree optic that really allows us to look at very long ranges. You're going to see an example of that coming up shortly. So here's an example of resolution and spot size. Here's just one example in a utility substation where we could see the hot spot. It's 41 degrees C with my 76,800 pixel camera. If I quadruple the resolution, whether in the camera or with another camera, I can see the problem, and my temperature went up about 4 degrees. If I go to my high performance camera that has 786,000 pixels, you can see a temp rise of 71 degrees. So you're starting to increase the temperature, which is important. You want accurate temperature measurement. I've added this one color photo because sometimes people like black and white. Some people like grayscale, or grayscale is black and white, excuse me. Some people like ironbow, which was the previous. In this example, I actually like rainbow. It's one of the few ones I do like rainbow because rainbow truly identifies where that heat is actually centered on this target, and the rest of the heat is conducting away. That's why that finger in this example looks warm. So here we're going to show off another example of what a high resolution optic or a telephoto optic can do for you. So here's an example of this electrical application. You're about 50 feet away. And I had the telephoto lens. My temperature just rose 4 degrees. So that's a 12-degree lens. So that's a 2x lens previous. Now let's take a look at the 6x lens. The 6x lens gives tremendous detail. As a matter of fact, such good detail, we can actually now identify where the weak link in this problem is. It's the upper right-hand bolt. The upper right-hand bolt is warmer than the other 3 bolts. It's probably loose, so resolution will help with identifying the problems as well. Here's the last photos of thermal resolution. This target's maybe 150 feet up in the air. It's really far away. So you can see the temperature right now is 66 C with a 76,800 pixel camera. If I add the 320 by 2, the 640 by 480 camera, we're up to 307,000 pixels, and that temp went up 77 degrees. And now I took the 786,000 pixel camera with the 2x lens, and now that temperature almost doubled. But I'm going to let you on a small secret. I actually cheated here. I'm actually using the Ultramax version with this. So this is actually an array size of 3.145 million pixels. This is as good a thermal imaging as you can get. So now that I've told you how great resolution is, I don't want you to forget about another important feature. That's sensitivity. Sensitivity is very important in generating the very best image possible. So when you think about your program, you know, a really good image helps customers understand what the problems are better. And that customer could be a client or it can be a manager to solve the problem. Think about this way. When you go into a Costco or you go into a store to buy a TV and you see all these 4K TVs or high resolution TVs, what is the difference between one TV versus the other when they're all claiming very high resolution? It's low noise and black levels with them. With us, it's just strictly low noise. So when you're doing your decision making, look for the NETD. The lower the NETD, which is the figure of merit for noise, the lower the number, the better. So if I look at these two images, the one on the image is a much cleaner image. I can see the studs in the wall, and I can see the nail pops in the wall. I'm having very difficult time doing that with a 320 by 240. If I improve on that, I can see now, by improving the sensitivity, I now see the nail pops a little bit better, and now I see the studs a little better. This is very helpful if you're doing, you know, predictive maintenance, facility maintenance, building diagnostics, where you are looking for subtle temperature differences. A reminder, the smaller the number, the better. Here's where you would see it on the spec sheets. Detector thermosensitivity, NETD, right there. Look for that on every one of the specs on any camera that you'd be considering or your old camera to see what one you actually have. Okay. So that's the difference between, you know, hardwares, how to improve hardware on these cameras. So there's three facets that I'd like to talk about, right? Well, three facets I have talked about. One is the camera, the other one's software, and the other one's people. So how do we improve the people performance of our technology? The way to do that is to help guide the operator on the path. So if you're talking about multiple points to inspect, it takes too long to finish. You're not sure what's next on the list to inspect. You're using pen and paper to document it. You're still doing it the old way. You know, maybe you have an inexperienced user. Maybe you have an experienced user who left, retired, moved on. Now you're stuck with who's going to now operate the camera. And report time is time consuming. Always has been. It shouldn't be anymore. But it is if you are not operating, if you're working harder, not smarter. And last but not least, a lot of these applications really benefit from historical data and how to analyze and keep that. So one new solution that's gaining popularity these days is merging the digital technology out there. What if I could tell you that now the camera and the software can work together? What if your camera now had GPS in it? And I don't mean like GPS that tells you where you are, but the GPS in your car, when you're going from point A to point B, it gives you the route to get there. Well, think about the route within your plant. How do you get from point A to point Z and hit every point in between efficiently every single time? Well, that technology now exists to really improve the efficiency of being able to have the camera tell an operator where to go. And once you get there, what to take a picture of. So here's an example of a system where the camera can start you at a certain point, then drive you to a subset within that point, and now you can go deep into this organization and now identify all the targets you want to see, store all the images that you want to take, and then have all this information at the ready. So now routing exists in the cameras. It doesn't exist in a third-party software. It doesn't exist on your iPhone. It's now built into the camera where you can hand the camera to an operator and just say, follow what the camera tells you. So now your inspections are efficient. You know, the cameras have touch screens. So you're now able to touch the screen and index from point A to point B to point C. Store the images, store the notes on the images. So a new or experienced user will have the same exact performance. And most important, the lexicon is the same. If you designate motor ABC, then it's always going to be ABC. You now never have to worry about each operator using their own slang or their own verbiage to describe something. You know how challenging that can be and how it can lead to errors if all of a sudden now people are using similar verbiage to describe the same exact thing. And consistency equals excellence. The easier it is to do something, the more repeatable you will be at it, the more consistent you will be at it, and finally you'll become, the whole program will be excellent and you will get the same performance day in and day out. The good news is the software there is receptive and is ready for you to bring in all the information on the route, where all you have to do is just drop and drag the images into the report and it'll create the report for you. Since the route text was already there, you don't have to type anything else out there. Since the route text was already there, you can search on the same exact words to pull up images that you've taken many times over the years. It's a wonderful archive system. And finally, this gives you the ability to spot trends within your facility. Are certain things failing all the time? Is this motor always tripping out at the same time? Infrared can help you if you have the archived data and it's easy to access. So that has recently happened where now customers can view their cameras not solely by themselves, but of a part of a system that can increase the reliability of your facility. Did you know that these cameras also have Wi-Fi built into them? And manufacturers like FLIR created apps where you can stream the data from your camera to your phone. So if you found the problem and you need to get that information out quickly, as we can see in this picture, this gentleman's taking a picture. He blew Wi-Fi'd it to his phone, and from his phone, he can analyze it, create the report on the fly, and email critical issues out immediately. Time can save a lot of money if you act quickly. These are built into the camera systems as well. And finally, the third most important piece in this whole system is the person, right? Knowledge of what they're doing, how to make an accurate temperature measurement. I would always recommend our customers take infrared training. If they're serious about their program, or if they want to learn more, there's plenty of online resources at FLIR and at the Infrared Training Center. You know, not only getting an accurate temperature measurement, but making that image look spectacular. We teach the art and the science to do that. Training's about physics. We want to eliminate any false positives that can be caused by reflective issues. It would be helpful if the student, the person operating the camera, knew the physics involved. And on top of that, we go over some basic typical predictive maintenance applications. So it's just not all book learning. You get to try within the labs that are provided at the training organization. And finally, there's also software support. The people are there to help you create the best program possible and how to get the most out of your camera, your software, yourself, and create a fine-tuned system. So in summary, the viewfinder is very helpful outdoors. I was in Grants, New Mexico a couple weeks ago. The sun was out. You couldn't see anything on your smartphone. And the customer out there said that you can't live without the camera, a viewfinder out there. So if you find yourself in sunny climates and you do a lot of work outdoors, look at a camera with a viewfinder. We talked about resolution and sensitivity is critical. It is. You know, getting the best for your operation will help you not only pay that back very quickly, but get the most out of your camera. This presentation wasn't long enough to go through all the fine details of the software. We wanted to hit the highlights. But we all know that software is a critical component of how you take the information that you see in the camera and translate that into, for your customers, your managers, the people that have to fix it. The easier it is to use, the better you'll be able to transfer that information and to keep justifying and showing payback for the investment you make. And last but not least, training ensures confidence and repeatability. As we talked about, we want to ensure the excellence of the program. At FLIR, nothing makes me sadder that customers buy cameras, then the person has left, and now it just sits in the closet. We want to see those cameras used every single day. There is no reason why, if you have a camera and someone's going out to take voltage measurement and you're not using the camera, you should. Because if you're taking a voltage measurement, you're looking at live equipment, and that camera could see that hot spot before that operator touches something. So don't lock the cameras up in the closet. Let the operators use it. These cameras are durable. They're not going to break it. And the more they use it, the more they'll embrace it. And then look to train your operators to get the most out of your system. I want to thank you for your time today for this short webinar. I really appreciate it. Nicole, are there any questions?
Yep. Thanks, Ed. So as a reminder, that concludes the presentation portion of the webinar. If you have any questions you'd like to ask, you can do so through the webinar controls. There's a question box, and you can submit it there. Let me see what we've got here. Okay, question, do all cameras come with routing software?
So currently right now, in the FLIR portfolio, the FLIR T series, which is the FLIR T530, 540, and above, all have that option for the routing software. So we're talking 6 models that have the ability today. Now, if you have an older T530, that camera platform's been out for about 2 years now, you have the option to get that feature put on your system. So the answer is, routing is new today, but if you've invested in a T series, let's say yesterday, you have access to it. All you have to do is just call Transcat, and they'll work with our service department to get you upgraded.
Okay, how high can cameras measure temperature? How high of temperature can they measure?
So that's a great question. You know, as you saw on the example, the camera that I had took that picture. That temperature was getting close to 1,000 degrees Fahrenheit. Camera temperatures generally go up to about standard range is 650. Then there's optional ranges up to 1,200 and 2,000, depending on the quality of the camera that you're looking at. So if you need to go to 2000 C, which is around 3700 degrees F, we can get you there.
Okay, how far can you be from an object to get a good temperature measurement?
That goes to the resolution question, and it really depends on the size of your target. Now, if I were to use a 320 by 240 focal plane array with a 25-degree field of view, and I was measuring a 1-inch spot, you could be roughly about 20 feet away. If I add a telephoto lens to a 2x lens, then I can be about 40 feet away. It really depends on the resolution. There are calculators on the FLIR website that will help you identify your target, the size, and what you want to measure. Just give a call out to Transcat and Nicole, and she'll get one of us on the line, and we can guide you through the proper selection dependent on the size of your target and how far away you are.
Okay, and are there specific cameras that come with the eyepieces for outdoor viewing?
So the newest FLIR camera that has an eyepiece is the FLIR T840. So we have the T500 class camera, but then the T840 is our newest camera line. It's our first, most affordable thermal camera under $20,000. It has an eyepiece, and it's perfect for outdoor use. Previous eyepiece cameras used to sell for around $26,000 to $30,000 to $50,000. This one's the first one that's affordable at below 20.
Great, thank you. All right, that concludes our time for today. If you have further questions that went unanswered, or you'd like to find out more about what Transcat offers in regards to thermal imaging cameras, you can contact us at 800-800-5001 or on the web at transcat.com, or you can email me directly at nvanward@transcat.com. Thank you for joining us today. Thank you, Ed. I appreciate it. We hope everyone got something out of the presentation and that you continue to join us for future Transcat e-learning webinars. Have a great day, everyone. Thanks, Ed.
Thank you. Bye.
Bye.